Yes, very good morning, my dear friends. Today we will start solving a few problems from the topic, as you already know, chemical equilibrium. Let us go to the first question here. 4.5 moles each of hydrogen and iodine were heated in a sealed 10-liter vessel. At equilibrium, 3 moles of HI were found. The equilibrium constant is. This is the simplest question. So let me first write the equation here. See here, what they have taken is 4.5 moles of hydrogen and iodine. Let me write the equation. Hydrogen plus iodine gives hydrogen iodide. That is the reaction. What they have started with is 4.5 moles each of hydrogen and iodine. So moles at start. Moles at start. In the beginning. This also is 4.5. This also is 4.5. This is 0 because it is yet to be formed. Because you have just started the reaction. Now, at equilibrium, moles at equilibrium. This is more important. What they are given? At equilibrium, it is only 3 moles of HI were found. At equilibrium, how many moles? 3 moles of HI were found. Now we have to make a little bit logic. See here, the equation says that for 2 moles of HI to get 1 mole of I2 and 1 mole of H2 has to combine. Now for getting 3 moles, so half of that means 1.5 mole of H2 and 1.5 mole of I2 should combine, giving double of that is 3 moles of this. So moles at equilibrium, 4.5 we took, of course. Out of that, 1.5 went because it gave hydrogen iodide. So also, this also we took 4.5 initially. Out of that, 1.5 went in the combination. So what is remaining? 4.5 minus 1.5 is 3. Then 4.5 minus 1.5 is 3. This is anyway 3, which is formed. These are the number of moles at equilibrium. Now, from number of moles, we have to change it to concentration. Concentration, how will you find? Moles divided by volume in liter. Volume of the solution in liter. Because concentration is moles per liter. They have given it is 10-liter vessel. So this becomes 3 by 10 mole per liter. Again, this also you have to divide by the same. Again, this also you have to divide by the same. Volume of the solution, volume of the vessel. Now, this obviously 0.3, this also 0.3, this also 0.3. These are the concentrations of each species at equilibrium. Now, what you have asked here? You have asked to find out the equilibrium constant. I shall write Kc here. Kc is, while writing the equilibrium constant, the product side should come in the numerator and the stoichiometric coefficients should appear as power. So here what I write is molar concentration of HI to the power 2, it is this number of moles, divided by molar concentration of H2 into molar concentration of I2. This is the expression, right? Now we will substitute this. So this is HI 0.3 of that square divided by this also is 0.3, this also is 0.3. So it is obviously it is a 1. So correct answer is option A is the right answer. Option A is the right answer. Equilibrium constant 1. 0.3 square divided by 0.3 into 0.3. So ultimately it will be 1. So option A is the right answer. Hope that it is clear. Now we will move on to the second question. Second one. 5 moles of PCl5 are heated in a closed vessel of 5-liter capacity. It is more or less on the same concept. At equilibrium, 40% of it is found to be dissociated. What is the value of Kc? What is the value of Kc? Once again, let us write the equation. PCl5. Okay. So, equation is, yes, PCl5 in equilibrium with PCl3 plus Cl2. This is the reaction. Then what they are given here? 5 moles of PCl5 are heated. So initial moles. This is 5 moles. This is yet to be formed. Right. Then what they are giving is, at equilibrium, 40% of it is found to dissociate. What is 40% of 5 mole? 40% of 5 mole, that becomes 2 moles. 2 moles undergoes dissociation. So what is more important for us is remaining. So initial, this is at equilibrium. At equilibrium measure, right? No doubt 5 we have taken. Out of that, 40% of 5 is 2 moles. 2 moles undergoes dissociation. What remains is 3 moles. What remains is 3 moles. Then where these 2 moles went in? See the reaction stoichiometry. 1 PCl5 gives 1 PCl3 and 1 Cl2. We have to obey the reaction stoichiometry. So here 2 of this has undergone dissociation, obviously giving 2 moles of PCl3 and 2 moles of Cl2. 2 moles of Cl2. Because we have to obey the reaction stoichiometry. Now, as I again tell you, to find out the concentration, each moles you have to divide by volume of the vessel in liter. They have given it as 5 liter. So, concentration at equilibrium. How will you find out the concentration? Number of moles you have to divide by volume of the container in liter. They have given it as 5. So, again this also is to be divided 5. This also is to be divided by 5. So, 3 by 5, it is as good as 6 by 10. So, it becomes 0.6. So, like that, 2 by 5, it is as good as 4 by 10. If you multiply both the numerator and denominator by 2, so it will be 4 by 10. 4 by 10 means it is 0.4. So, again this is, so 2 by 5 means 0.4. Okay. What they have asked is value of Kc. How will you write Kc expression? Kc expression, always the product side should come in the numerator. Concentration of PCl3 into concentration of Cl2 divided by concentration of PCl5. This is what you have to write. Now let us substitute. Concentration of PCl3 is 0.4 into concentration of this is Cl2 is again 0.4 divided by concentration of PCl5 is 0.6. 0.6. This is what we got. Right. So here, if you divide it like that, so 0.22 za, 0.23 za, 2 into 0.4, 0.8 by 3, 0.8 by 3. Oh, okay, 0.8 by 3. Or it is 0.32 za 6, right? Then remains 6, 3, 6 the 6, like that it continues. So, mole per liter, unit is mole per liter, because 2 concentration terms are there in the numerator, 1 in the denominator, so you will get a mole per liter. So, option is again A is the right answer. So, 0.266, that's the answer. So, this is a simple problem. Now, we will move on to problem number 3. Problem number 3. For the equilibrium reaction, calcium carbonate, calcium oxide plus CO2, Kp they are given, 50 grams of calcium carbonate in a 10 liter closed vessel is heated to 100 Kelvin. Percentage of calcium carbonate that remains unreacted at the equilibrium. So this is a little higher level problem. We will solve higher level problem so that easier problems will be, you can solve it very fast. So this is the reaction they are given, isn't it? Equilibrium constant they are given. Now, let me once again write the reaction. CaCO3, it gives solid, gives in equilibrium with CaO, which is a solid, plus carbon dioxide, which is a gas. This is the reaction. Now, how will you write the equilibrium constant? So, while writing the equilibrium constant, product side should go to the numerator. And one more thing is, any pure substances, may be solid or liquid, they have to be just ignored because their activity is taken as a 1. So here, Kp becomes partial pressure of CO2. That's all. Because that is the only gaseous product. Both are solids, but ignore them. That they have given how much? It is 1.64 atmosphere. So that they have given it as a 1.64 atmosphere. 1.64 atmosphere. Okay, that they have given. Now, so you have an equation. PV is equal to nRT. PV is equal to nRT. I want to calculate the number of moles of this 1.6. So N is equal to PV by RT. N is equal to PV by RT. How much pressure shall we put here? See here. It is pressure is okay 1.64 atmosphere. That is the pressure. 1.64 atmosphere. Volume is how much? Volume is it is 10 liter. Volume is 10 liter. 10 liter. Remember the value of volume you have put it in liter. So obviously R should be 0.082. So you should not put it as 8.314. It should be 0.082 because 0.082 liter bar per Kelvin per mole. You have to put this. Then T is 1000 Kelvin. Right. We'll simplify it. See, 10, 10 gone here. So it is 1.64. This I shall keep it as it is. 100 means 10, then 8.2. 8.2. It were 16.4 by 8.2, it would have been 2. It is 1.64 by 8.2, so it is 0.2. So 0.22 mole of carbon dioxide are present. Now see the equation. Number of moles of carbon dioxide is equal to number of moles of calcium carbonate decomposed. Number of moles of carbon dioxide formed. Isn't it? 1 mole is equal to number of moles of calcium carbonate decomposed. Calcium carbonate decomposed. That means 0.2 mole of calcium carbonate is decomposed. Agree? Number of moles of carbon dioxide formed is equal to number of moles of calcium carbonate decomposed. So we got 0.2 moles of carbon dioxide. It means 0.2 mole of calcium carbonate is decomposed. Then how much remains undecomposed? So calcium carbonate remaining undecomposed. Calcium carbonate remaining undecomposed. Yes, how much is undecomposed? How much we have taken? We have taken moles of calcium carbonate, right? Moles of calcium carbonate taken. Carbonate taken. How will you find out mole? Mass in gram by molar mass. Okay. Mass in gram is 50. Molar mass of calcium carbonate will be 100. If you work it out, calcium 40, carbon 20, then carbon 12, of course. Then O3, 16 into 3, like that it comes 100. So it is 0.5. So out of 0.2 underwent decomposition. So calcium carbonate remaining undecomposed is 0.5 that is taken minus 0.2 that is decomposed. It is 0.3. 0.3 is remaining out of 0.5 mole. What we have taken? 0.3 remains undecomposed. Therefore percentage. If it is 0.5, we have got 0.3 undecomposed. If it is 100, for 0.5, 0.3. So if it is 100, so it comes to 0.3 by 5 means 3 by 5. 3 by 5 it is as good as 6 by 10. 6 by 10, 100 cancels. So 6 into 10, that is 60% of calcium carbonate remains undecomposed. 60% of calcium carbonate remains undecomposed. So the answer is option C. Option C is the answer. Option C is the answer, 60%. Hope that you understood. So what you have to do is, you have to write the expression for Kp. Then for this, since these two are solids, so the Kp itself will be partial pressure of carbon dioxide. We got it 1.64 atmosphere. From there, using the formula P is equal to nRT, we calculated the number of moles, considering the volume, etc. So it became 0.2 moles. Number of moles of carbon dioxide formed is equal to number of moles of calcium carbonate decomposed. That means 0.2 moles of calcium carbonate decomposed. Calcium carbonate taken. How will you find out the number of moles? Mass in gram by molar mass. Mass in gram is 50 gram. Molar mass is 100. So we have taken 0.5 mole. Out of that 0.2 underwent decomposition. What remains undecomposed is 0.3. Then finally what they have asked is percentage. So out of 0.5, 0.3 decomposed, then 100. It is 60%. So answer is it is A. Yes. Next question. Yes, fourth one. Kp value for the reaction is at 460-49. If the initial pressure of both hydrogen and iodine is 0.5 atmosphere, then what will be the partial pressure of hydrogen at equilibrium? What will be the partial pressure of hydrogen? So let me solve here. Yes. So H2 plus I2 giving 2HI. 2HI. Right. What are you given? Initial pressure is, initial pressure, if pressure of both, it is 0.5. Initial pressure. Initial pressure, this is also 0.5, this is also 0.5. This is 0 because it is yet to be formed. We don't know out of 0.5 how much undergoes dissociation. Let us hope that out of 0.5 X undergoes dissociation. So decrease in the pressure will be by X. So this is equilibrium pressure. Equilibrium pressure. Okay. 0.5 we took. Out of that let X go. Reaction stoichiometry says that moles of H2 combined with equal moles of I2 giving double of that of HI. So this also should be 0.5 minus X. Same quantity will be. So if X of this goes, this will be double of that will be formed, 2X will be formed. 2X will be formed. Then how will you write Kp for this? Kp is equal to, I don't want to write the expression, partial pressure of Hi of that square product side. Partial pressure of H2 into partial pressure of I2. That's what I have written. Now let me substitute. Partial pressure of Hi, 2x whole square divided by, both are 0.5 minus x, 0.5 minus x. I can write it as 0.5 minus x whole square. This is equal to, they have given it as a 49. This they have given it. So if squares appear like this, what the best way is taking the square root. You have to take the square root of both the sides. If you take the square root of both the sides, this side it will be 2x by 0.5 minus x. Square root of 49 is 7. This is the best way of simplification. Now cross multiply, 2x is equal to, so it is a 0.5 into 7, 3.5 minus, so x into 7, 7x. If you bring it to this side, so 9x is equal to 3.5. 9x is equal to, correct? Minus 7x, if you bring it to this side, it will plus 7x. 2 plus 7, 9x is equal to 3.5. On solving x is equal to 3.5 by 9. 3.5 by 9. Yes, point, correct? So 9 3s are 27, 27. Okay, so then what remains? 9 3s are 27, 27, then 35. So 9 6 is a, so 9 8 is a, again 9 8 is a, like that it will. It continues like right now. This is x. What they have asked is partial pressure of H2. Partial pressure of H2 is equal to, partial pressure of H2 is equal to 0.5 minus x. So 0.5 initial, out of that minus 0.388. Minus 0.388. Correct now? 0.5 we took it initially, then 0.388 that is reduced because it underwent combination giving HI. So what remains is 0.112. 0.112. So the answer is 0.112. So that is option A. Option A is the answer. 0.112. That is the partial pressure of hydrogen. Partial pressure of hydrogen. So hope that you have understood it. So once again I shall tell. So equation, initial pressure, both 0.5 each. Out of that, let x undergo combination. So x decrease, this x decrease, double of that of this is formed. Then write an expression Kp. Then simplification, take the square root of both the sides. Then on simplification, you got x as 0.388. X is the amount that is consumed. Now, what is asked is remaining partial pressure of H2. 0.5 we took minus 0.388. What remains is 0.112. That is option A. Option A. Next one. For NO, 2NOBr, 2NO plus Br2, right? At equilibrium, partial pressure of Br2 is P by 9. P is the total pressure, the ratio of Kp by P, the ratio of Kp by P. So let me write the equation again. 2NOBr giving, 2NOBr giving, 2NOBr, right? 2NOBr, that is it. What they are given? Gas. It decomposes giving 2NO, which is a gas, plus Br2, Br2. Okay, this Br2 is also gas. Right now, at that temperature, it's a gas. Of course, bromine is a liquid at room temperature, but at that temperature, it's a gas. Let us hope like that. What they have given? Partial pressure of Br2 is P by 9. P by 9. See the reaction stoichiometry. How much of Br is formed? Double of that 2NO Br. It is double of that NO. So, partial pressure of NO, it is 2P by 9. 2P by 9. Right? So, this is the partial pressure at equilibrium. Then how much was taken? Initial pressure was P. Initial pressure was P. Out of that, so initial pressure was P. Out of that, 2P by 9 and P by 9 was decreased. So remaining is P minus 2P by 9 plus of this P by 9. Right, P we took initially. So out of that, so this pressure became 2P by 9. So this is P by 9. So remaining will be P minus 2P by 9 plus P by 9. So if you simplify this, P by 9, okay, 2P by 9 by P by 9 is 3P by 9. P minus 3P by 9. P minus 3P by 9. Isn't it? This is the remaining pressure of this. So again, LCM is 9. LCM is 9. So it is 9P minus 3P. 9P minus 3P. That is 6P by 9. 6P by 9 is 3 2s are 3 3s are. You can write 2 by 3P. 2 by 3P is the partial pressure of NOBr. Then of this is 2P by 9. This also P by 9. Okay. Now let me write the expression for Kp. Kp is, I will write partial pressure of NO of that square into partial pressure of bromine. Here did not write square because only one mole. Divided by partial pressure of NOBr. Again, tell me what you have to write. I have to write square because here 2 moles. Now we will substitute. Substitute. Partial pressure of NO. Partial pressure of NO is 2P by 9. Correct? 2P by 9. Okay. Of that square, I shall write here itself into 2P by 9. Okay. Square I have completed here only. So 2P by 9 square into partial pressure of Br2. That is P by 9 into divided by partial pressure of NOBr divided by partial of NOBr twice. So what I write is, so here into I shall write 3 by 2P into 3 by 2P. Hope that you have understood. Correct now? It should be divided by 2 by 3P square. So what I have written is into I have written. Then I have just changed the numerator and denominator. Then I have written like this. Now, what we can say? 3 into 3, 9. 190. 2p, 2p. This 2p, this 2p gone. So what remains is p by 9 into 9, 81. P by 9, 81. Right? This is the equilibrium constant. What they have asked is, they have asked, therefore, Kp by P. Kp by P. This is Kp. P by 81. By P means 1 by P. P gets cancelled. The answer is 1 by 81. The answer is 1 by 81. That is option D. Option D is the right answer. 1 by 81. Hope that you understood. Once again I said it. What they are given is, equation they are given, and they are telling partial pressure of bromine is P by 9. Equation it says that double of that this should be formed. Here it is 2. So initially was P. From that you have to subtract the pressure of these two. Total pressure was P. Right? So you got all this. Then expression for Kp we wrote. Substituted the values. We got Kp is equal to P by 81. What we have asked is Kp by P. P by 81, that is Kp divided by P. Pp gets cancelled. So 1 by 81 is the right answer. Hope that you have understood it. We will move on to question number 6. See, 5 moles of SO2 and 5 moles of O2 are allowed to react. At equilibrium, it was found that 60% of SO2 was used up. If the total pressure of the equilibrium mixture is 1 atmosphere, the partial pressure of O2, Okay, so read the question carefully, because when I switch on to the next slide, question will not be there. 5 moles of SO2, 5 moles of O2. Yes. SO2 plus O2 giving 2 SO3. In order to balance 2 and 2 you want. Of course, all are gases. This also gas, this also gas, this also gas. Initial how many moles? Initial how many moles they have taken? Initial 5 moles of SO2 and O2. 5 and 5. This is yet to be formed. Then they are telling at equilibrium 60% of 5. What is 60% of 5? 60% of 5. That is 3 moles. 3 moles of what? 3 moles of SO2 undergoes combination. So at equilibrium, how much? 3 of SO2. 5 we have taken. Out of that, 60% means 3 moles undergoes combination. What remains is 2. Correct. See the stoichiometry. So oxygen required is half that of SO2, because 2 SO2 and 1 O2. Since 3 of this is used up, so oxygen that is used up is half of that, is 1.5. So remaining is 5 we took. Out of that, 1.5 underwent combination. How it becomes 1.5? Because if sulfur dioxide is 2, oxygen needed is 1. Sulfur dioxide used up is 3, so oxygen required is half of that is 1.5. So 3 moles of SO2 is used up. Number of moles of SO2 is equal to number of moles of SO3 formed. So this is, of course, so 5 minus 1.5, so it is 3.5. Number of moles of SO2 is equal to number of moles of SO3 formed, 2. So this is 3, so this also should be 3. So these are number of moles at equilibrium. Then what shall we do? Okay, if the total pressure is, we will find out the total number of moles. Total number of moles. When? At equilibrium. You have to sum it up. 2 plus 3.5 plus 3.5. 3 plus 3, 6. 6 plus 2, it is 8.5. Understood? 3 plus 3.5, it is 6.5. Then 2, 8.5. Then we will move on to what they have asked. So total pressure at equilibrium, they have partial pressure of O2. Now we will find out mole fraction of O2. For mole fraction, X is the symbol. Mole fraction of O2, number of moles of O2 divided by N total. Number of moles of O2 is 3.5 divided by total number is 8.5. 3.5 divided by 8.5. So 3.5 by 8.5. So that will be 0. This is partial pressure, mole fraction. Partial pressure of O2 is mole fraction of O2 into P total. Fortunately, P total they have given it as a 1 atmosphere. So this itself is 3.5 by 8.5 into 1. They have given under 1 atmosphere. If you work it out, so it will be 0.41. If you simplify it, it will be 0.41. So 0.41. Option D is the right answer. Option D is the right answer. 0.41 is the answer. Hope that it is clear. Okay. So once again, you have to go through all the problems. Understand? Try to solve them independently and get the answer. Now we will move on to the next one. Next one. 2.2 moles of PCl5 were taken in a closed vessel and dissociated into PCl3 and Cl2. At equilibrium, the total number of moles of the reactant and the product was 2.53. Degree of dissociation. What do you mean by degree of dissociation? Out of 1 mole, how many moles undergo dissociation? That is degree of dissociation. So let us take it as X. Okay? Yes. PCl5. So what is the reaction? PCl5 gas gives PCl3 plus Cl2. All are gases. Right now, what they have taken? Initially they have taken 2.2 moles of PCl5. Initial 2.2 moles. Let X be the degree of dissociation. Degree of dissociation. Let it be X. Means out of 1 mole, X goes dissociation. If 2 moles were taken, 2X will mole undergo dissociation. Right? So what they have taken is 2.2 moles. So from 2.2, 2.2X undergoes dissociation. Because we have assumed X is the degree of dissociation. Right? 1 mole, X goes. If 2 moles were taken, 2X goes. Since we have taken 2.2 moles, the number of moles of PCl5 undergoes dissociation is 2.2X. 1 PCl5 gives 1 PCl3 and 1 Cl2. This also should be 2.2X. This also should be 2.2X. Then let me write total number of moles at equilibrium. You have to add all this. If you add, 1 goes. So it will be 2.2 plus 2.2X. Right? This they have given it as 2.53. That they have given it as a 2.53. So in this, if you solve for X, I don't want to give much time for simplification. So it is algebra. Solve for X. So X will be 0.15. If you simplify and solve for X, X will be how much? 0.15. That is the degree of dissociation. So option is C. C is the option. 0.15. Here a little I have given it for you. You have to simplify it for X. Just shift it and X will be 0.15. That will be the degree of dissociation. That's the answer. Yes. We will move on to 8th question. See here. 2HI plus H2. The equilibrium constant of the above reaction is 6.4 at 300 Kelvin. 0.25 mole of each of H2 and I2 are added to the system at the same temperature, then the equilibrium constant will be. Remember, my dear friends, if the temperature is kept constant, you add any substance, equilibrium constant remains unchanged. Right? So all this data, 0.25 mole FH2I2, that is just to take you to the wrong side. If you know it perfect, so at the same temperature, this is more important. At the same temperature, equilibrium constant remains same. So 6.4 itself is the answer. 6.4 itself is the answer. Option A is the answer. Right? So just remember, as long as the equilibrium constant remains same, the temperature remains same, equilibrium constant also remains same. So we will move on to Next one, that is the ninth one. 2 moles of N2O4 is kept in a closed container at 298 Kelvin under 1 atmosphere pressure. It is heated to 596 Kelvin when 20% by mass of N2O4 is decomposed. Let me write the reaction. Yes. So N2O4 gas. Yes. Giving 2NO2. Reaction stoichiometry is very important. What they have started with is, they have started with, how much? 2 moles. Moles at start. Moles at start. This is 2, this is 0. Because start. Then they are telling that at equilibrium, 20% of mass is reduced. 20% of 2 mole. 20% of 2 mole, it is a 0.4. Right now, 0.4 undergoes decomposition. So what remains is, at equilibrium, 2 we have took, out of that how much undergoes dissociation? 0.4. See the reaction stoichiometry. Double of this is NO2 form. The reaction is like that. So since 0.4 of this undergoes decomposition, this form will be double of 0.4. That will be 0.8. 0.8. Now, let me find out the moles at equilibrium. Moles at equilibrium. 2 minus 0.4 plus 0.8. It will be 2.4 moles. Right now. So, initially, when the number of moles was 2, for 2 moles of the gas, pressure was how much? Pressure was how much? For 2 moles of a gas, pressure was 1 atmosphere. 1 atmosphere. They are given 2 moles of a gas under 1 atmosphere. When the number of moles changed from 2 to 2.4 moles, pressure becomes how much? It is, for 2, it is 1 atmosphere. For 2.2 moles, it is 1.2 atmosphere. Remember, this 1.2 atmosphere is at 298 Kelvin. 298 Kelvin. So simultaneously, what they have done is, they have changed the temperature also to 596 Kelvin. So according to Gay-Lussac's law, what it says? P1 by T1 is equal to P2 by T2. This is Gay-Lussac's law. So when the temperature was 298, pressure was 1.2. So when the temperature is 596, what will be the pressure? This is a question now. See here, temperature is doubled. So obviously, pressure also is to be doubled. So the answer is 2 into 1.2, that is 2.4 atmosphere. This is the answer. 2.4 atmosphere is the answer. That is option B. Option B is the right answer. I'll tell it again. See here. 2 moles they have taken. Then they are telling that 20% of that, that is 0.4, undergoes decomposition. Double of that it is formed, 0.8. Total number of moles will be 2.4. So when the pressure, 2 moles, for 2 moles, the pressure was 1 atmosphere. So when the number of moles changes from 2 to 2.4, pressure obviously should go to 1.2 mole. 1.2 mole atmosphere, it is at 298 Kelvin. Since they have doubled the temperature, the pressure also should be doubled. That is Gay-Lussac's law. P1 by T1 is equal to P2 by T2 in a confined volume, when the volume is fixed. So P1 by T1 is equal to P2 by T2. This is what we call Gay-Lussac's law of combining volumes. Yes. Next one. See. Reaction A plus B giving rise to C plus D initially was started with equal concentration of A and B. At equilibrium, number of moles of C was found to be twice that of A. The equilibrium constant is. So very easy it is. A plus B, A plus B in equilibrium with C plus D. They are taken both in equal quantity. And reaction stoichiometry says that both will combine in equal moles. Both will combine in equal moles. Right. So at equilibrium, if this is X, okay, so moles, number of moles of C is twice that of A. If it is X, C will be 2X. So since they are taken both in equal quantity, if X of A remains, X mole of B also should remain. Since these two are formed in equal quantity, how much of C is formed, so much of D should be formed. Each also should be 2X. Equilibrium constant, Kc is equal to molar concentration of C, molar concentration of D, molar concentration of A into molar concentration of D. 2X into 2X by X into X. X gets cancelled. So it is a 4, option C. Very simple question. Very simple question. Okay. So for everything you have to refer the reaction stoichiometry, the moles which has been indicated in the reaction that you have to follow. Okay. Yes. The next one. See, if the concentration of OH minus ion in the reaction FeOH thrice solid, this is aqueous, this is aqueous. Okay. Concentration of OH is decreased by 4 times. Yes, the solid here. FeOH thrice solid, very important, giving Fe aqueous plus 3 OH minus aqueous. How do you write equilibrium constant? That is concentration of Fe plus 3. You need not write any power because it is 1 into concentration of OH minus to the power 3. This you have taken out. A pure substance, solid or liquid, it is to be. What they are telling is this concentration is reduced by 1 by 4. So the 1 by 4, since it is thrice, right? That coefficient by which K is reduced is 1 by 64. Right? 4 cube is 64. So the coefficient which is reduced due to this decrease in the concentration of OH minus is 1 by 64. In order to keep this K constant, obviously the next multiplicand should be increased by 64. When that is increased by 64, this 1 by 64 gets cancelled. Right? So the answer is, so option C. So this should be increased by 64 times. When this is increased by 64 times, this decreased by 1 by 64, that is 1 by 4 cube, that will be nullified so that the equilibrium constant remains as it is. So the right answer is option C. Option C. The rate constant for forward and backward reactions, it is very simple. So I shall write it here itself. Equilibrium constant is equal to rate constant for forward by rate constant for backward. Is the equation. Rate constant for forward is how much? It is 1.1 into 10 to the power minus 2 by rate constant for backward reaction is how much? 1.5 into 10 to the power minus 3, or it will be 11 by 10 to the power minus 3 when it went to the numerator plus 3. So 11 by 1.5. 11 by 1.5. So 11 by 1.5, it is 11 by 1.5 is 7.33. 7.33. Option D is the right answer. Very simple question. Of course, this was the question which was asked in your CET only, but long back. Now, you can't expect such easy questions. Questions will be a little of higher level. Right? Right? So, equilibrium constant is a rate constant for forward reaction divided by rate constant for backward reaction. Right? So, that's the answer you got. Yes. We'll move on to the next question. Next question. Yes, this is very easy. For the reaction Kp by Kc. So, relationship between Kp and Kc is Kp is equal to Kc into RT to the power delta Ng. Okay. How will you calculate delta Ng? Delta Ng, Ngp number of moles of product, number of moles of gaseous product, minus NG, NGP. NGP is 1, right? Product. Number of moles of gaseous reactant is 2. It is minus 1. So value of delta Ng is minus 1. So Kp is equal to Kc into RT to the power minus 1, or Kp by Kc is equal to RT to the power minus 1, or it is as good as saying 1 by RT. 1 by RT. Option A is the right answer. 1 by RT. Option A is the right answer. So very simple question. Very simple question. Yes. Next, of course, it is almost same type. So 13th one, 13th one we completed. 14th one, the value of Kp. Yes, here PCl3, Cl2 plus PCl5. Again, delta Ng will be how much here? Delta Ng, number of moles of gaseous product 1 minus number of moles of gaseous reactant 1 plus 1. Okay, that is minus 1. Minus 1. So here Kp is equal to Kc minus 1 is by RT. Kp is equal to Kc by RT. What they are given? They are given Kc value they are given. Kc value they are given. Kp you have been asked to find out. Kc value is 26. Okay. R you have to find this value only 0.082, because 0.082 liter atmosphere. So here mole per liter, when liter comes, this unit itself you have to take. Temperature is how much? 250. It should be in Kelvin only. 250, 273. Okay, 3 to 523. 523. 523. Okay. So if you solve this, it will be 0.61. 0.61. Right? Kc, we have substituted. R value, this one it should be. Then temperature, it should be Kelvin only. You can't compromise for that. If you simplify, it will be 0.61. 0.61. Option A is the right one. Option A, 0.61. Option A is the right one. Yes. Next, we will go to, yes, see. Equilibrium constant. Here, what we have done is, see here. See the two relations, reactions. SO3 plus gives SO2 plus half O2. This, they have reversed it and they have doubled. Since they have reversed, the new equilibrium constant, I shall write K dash. Since it is reversed, 1 by old equilibrium constant. And at the same time, they have doubled the quantity. All the quantities have been doubled. So, square. Right? So, why I have written K in the denominator? Because they have reversed. Right? If it is as it is reversed, then 1 by K was sufficient. So, they have reversed it and doubled the quantity. 1 by K square. That is 1 by, what is K? 1 by 4.9 into 10 to the power minus 2. 4.9 into 10 to the power minus 2. Okay? So, it is more or less 10 to the power minus 2. When it goes to the numerator, it is how much? 1 divided by 4.9 into 10 to the power minus 2. If you work it out, of that square, 4.9 into 10 to the power of that square, if you work it out, it will be more or less like 10,000 by 50, something like 400. The right option, it is 416. 416, option D. Understood? So, we have reversed it, and at the same time, all the quantities have been made double. So, reversing means denominator it comes. Then square, since the quantities are double, square. So, this equilibrium constant given you substitute and simplify, it will be 416. Yes. Next one. It is again same thing. N2 plus 3H2 2Na3. Okay. The equilibrium constant for the reaction, very simple. What they have done? They have reversed it because Na3 is in the product side. Here Na3 is in the reactant side, reversed it, and they have made all the quantities half. Reversed it means new equilibrium constant, the initial equilibrium constant should come in the denominator. Then they have made the quantities half, though you have to find the square root. You have to find the square root. Option D is the right one. Option D is the right one. It's very simple. Okay, reverse, so it comes in the denominator. They have made the quantities half, so you have to take the square root of that. You have to take the square. Very simple. Option D is the right answer here. Option D is the right answer. Yes. Next question. It's a very good question. See here. 3 equilibrium constant they are given, and what they have asked is the equilibrium constant for the oxidation of ammonia by oxygen to give NO. Yes, let me try this. Oxidation of ammonia to NO plus water. To balance this, H2, 3, this should be 2. 2NO. 2NO. Then O2, how much? O2. So here O2, 3, 2, 5 by 2. So let me write like this, 5 by 2. Of this we want the equilibrium constant. What they are given? First one what they are given is N2 plus 3H2. N2 plus 3H2 giving 2Na3. They are given. 12. See here, of this it is K1. What we want is ammonia in the reactant side. So quantity is same, 2. We want ammonia in the reactant side. So reverse this equation. So 2NO3, okay, gives N2 plus 3H2. What the equilibrium constant? 1 by K1. Why it should be 1 by K1? Because I have reversed it. Keeping the quantity same, I have reversed it. Why I have to reverse it? Because here in this equation, Na3 is in the product side, I want it in the reaction side. Come on, the second equation. NO plus O2. NO plus O2 giving 2NO. 2NO. Yeah, of course 2NO we want it in the product side only. Okay, here the equilibrium constant is K2. K2. Okay, then third one, H2 plus half O2 gives H2. H2. Of this K3. Of this K3. How many H2O we need here? 3 H2O. We have 1. We want 3. Of course, in the product side only. So, this equation you multiply by 3. So that you get 3H2 plus 3 by 2 O2 giving 3H2O. Okay. When the equation is multiplied by 3, you have to get the new equilibrium constant K3 cube. K3 cube. Now what you have to do? You have to add this equation and this equation and this equation. These 3 equations you have to add. When you add these 3 equations, obviously you get the required equation. It is more or less like solving the problems in thermochemistry, right? So when you add these 3, one equation, then this is second equation, this is third equation. When you add the 3, you get the required equation. When the final equation is obtained, by addition of the 3, the equilibrium constant is obtained by the multiplication, not by the addition, multiplication. So which comes here? K2 in the numerator, you have to multiply, K3 cube in the numerator, then K1 in the denominator. K1 in the denominator, because it is 1 by K1. So what is the right answer? Right answer is option B. Option B. This was asked in NEET couple of years back. This is a NEET question. You understood? First write the required equation. Because of that, for that, what equations, in which way you have to manipulate? Do it. Write the new equilibrium constant. By adding the 3 new reactions, if you get the required one, the equilibrium constants are not to be added, they are to be multiplied. They are to be multiplied. So, option B is the answer. Yes. Next one. Next one. In which of the following reaction is Kp greater than Kc? I shall tell you. Kp is equal to Kc into RT to the power delta N. Right? If delta N is greater than 0, very easy. Kp is greater than Kc. Same sign continues. If delta n is less than 0, Kp is less than Kc. If delta n is equal to 0, Kp is equal to Kc. Very easy. Same sign continues. Same sign continues. If delta n is less than 0, Kp greater than 0, Kp is greater than Kc. Less than 0, Kp is less than. What I have asked you? In which of the following reaction is Kp is less than Kc? Kp is less than Kc. Delta n should be greater than 0. Delta n should be greater than 0. So delta n is greater than 0 in which case? See here, reactant 1 plus 1, 2, product. Okay, so product, correct? So in this option 3, option C, what is delta Ng? Ngp minus Ngr. Ngp is how much? Gas 1 plus 1, 2 minus R, reactant how much? 1 plus 3, 4. So delta Ng is minus 2. Minus 2 means it is less than 0. Isn't it? Minus 2 is less than 0. Less than 0. So Kp is less than Kc. It is option C. Option C. You have to calculate delta Ng. Okay, that's a simple one. Yes. Next one, see here. Yes. See here. For the reaction N2O4 giving 2NO gas, the degree of dissociation of equilibrium is 0.2 at 1 atmosphere pressure. The equilibrium constant. Okay. Yes. Let me solve. So N2O4 giving 2NO2. N2O4 giving 2NO2. What they are given? Degree of dissociation at equilibrium is 0.2 at 1 atmospheric pressure. Degree of dissociation is 0.2 they are given at 1 atmospheric pressure. Okay? Yes. How will you solve it? Yes. So initial pressure is how much? Initial pressure 1 atmosphere, right? And they are telling degree of dissociation is 0.2. So at equilibrium, 1 minus 0.2. See the reaction stoichiometry. Double of this is NO2 form. Since this is 0.2, this form should be 0.4. This form should be 0.4. So then P total is how much? P total. This is 1 minus 0.2 plus 0.4, that is 1.2. P total is how much? 1.2. Then mole fraction of N2O4. We want mole fraction of N2O4. Mole fraction of N2O4. Mole fraction of N2O4, how will you find out? Number of moles divided by total pressure. Number of moles of N2O4 be by total number of moles. N total. Number of moles of N2O4 is 0.8. Correct? 1 minus 0.2 is 0.8. Total is 1.2. So 4 2s are, 4 3s are, it will be 2 by 3. It will be 2 by 3. 4 2s are 0.8, 4 3s are. Similarly, number of moles of which one? NO2. Number of moles of NO2 is equal to. Number of moles of NO2 is how much? I want directly, let me calculate partial pressure. Number of moles is 0.4. 0.4, isn't it? Divided by total number of moles is how much? 1.2. 0.4 by 1.2, it becomes 1 by 3. 4 ones are 1 by 3. 1 by 3. Then how will you write Kp for this? Kp is equal to partial pressure of NO2, okay, of this square divided by partial pressure of N2O4. Yes. Since the pressure is 1 atmosphere only, since the pressure given is 1 atmosphere, so total pressure is, partial pressure is mole fraction divided by, mole fraction into P total. P total is 1. So mole fraction itself becomes partial pressure. So partial pressure of this is N2O, NO2 1 by 3 square, let me write like this, into 1 by 3 square NO2, right, divided by N2O4, let me write 3 by, what shall I write? 2. Instead of dividing by 2 by 3, 3 by 2. 3 gets cancelled. What remains is 1 by 6. 1 by 6. So it is a 1 by 6. I'll tell it what it is. Initial pressure is 1. They are telling that 0.2 degree of dissociation, 0.2 goes. So this 0.2 appears in the form of NO2, double of that, NO2, 0.4. Now total number of moles is 1.2. Mole fraction of N2O4 is number of moles of N2O4 divided by total number of moles, 2 by 3. As here, since the pressure is 1, actually partial pressure is mole fraction into pressure. Since the pressure is 1 atmosphere, here you multiplying by 1, keep it remains same. So what we did is we substituted and then we got it as 1 by 6. Option C is the right answer. Option C is the right answer. Yes, next one. Which one of the following reaction will not get affected in increasing the pressure? Where delta Ng is equal to 0. That is not affected by change in the pressure. In which case delta Ng is not equal to 0? Option C. Option C. See here, 2 plus 1, 3, 2 plus 1, 3. Option C, delta Ng is equal to 0. So it is not affected by change in pressure. So option C is the right one. Option C is the right one. Yes. Next one. When I2 dissociates to give atomic hydrogen, see here, delta H plus means endothermic, delta H minus means exothermic. All endothermic reactions are favored by high temperature. All exothermic reactions are favored by low temperature. Le-Chatelet's principle. So this is endothermic because delta H is plus. So it is favored by high temperature. Option B is the right one. Option B. Simple one. Okay. Option B is the right one. Yes. Next one. Equilibrium constant for the reaction 100. If the initial concentration of all the 4 species were 1 mole each, then equilibrium concentration D. Yes. 1 mole each. Right? 100 equilibrium constant. A plus B. Let me write. A plus B giving rise to C plus B. Initial all are 1. 1, 1, 1, 1. At equilibrium we don't know. So out of that, let X undergoes dissociation at equilibrium. This is 1 minus X. X undergoes dissociation. This also will be 1 minus X undergoes dissociation. This will be formed. To this one, X will be added by forming. So this one, X will be added. Then how will you write the equilibrium constant for this Kc? That is A into B. I shall write 1 plus X square divided by A plus B. This into this 1 minus X square. That is 100. So as I told you that time, if square appears in both the sides, what you have to do is take the square root. If you take the square root, it will be 1 plus X by 1 minus X is equal to 10. 1 plus X by 1 minus X, it will be equal to how much? It is 10. 1 plus X by 1 minus 10 is equal to 10. Now, if you solve for X, X will be 0.82. Therefore, X will be 0.82. So I don't want to waste much time for simplification. So if you simplify, this is just algebra. Solve for X, it is 0.82. What they have asked is equilibrium concentration of D. Equilibrium concentration of D, one we have already taken. To that, this is added by the formation. It is 1.82. Equilibrium concentration is 1.82. Again, option D. Option D. We tell it once again, dear friends. Initially taken 1, 1, 1, 1. They have given. We don't know how much undergoes decomposition. So out of that, let x go. Since they are in equimolar, this also should be decreased by x. This is x form, which will be added to this. This is x form, which is added to this. We write the equilibrium constant, we get this 100 they are given. So take the square root, you will get this 10. On solving x, you get it as 0.82. What they have asked is equilibrium concentration of D, 1 plus x, 1 plus this x, 1.82. Option D is the right answer. Option 1.818, option D. Now, next one. In manufacture of ammonia by Haber process, see here. If it is in continuation, heat quantity plus means exothermic. Delta H will be minus exothermic. So it is favored by low temperature. One thing, low temperature. So low temperature, high temperature gone, high temperature gone, out of these two. Forward reaction is accompanied by 1 plus 3, 4 moles become 2 moles. Forward reaction is accompanied by decrease in number of moles, decrease in pressure. So if such a reaction should be made favorable, you have to make use of high pressure. So low temperature and high pressure. Low temperature and high pressure. Option C is the right answer. For ammonia formation, low temperature and high pressure, they are the two favorable quantities. Yes. Yes. The next one. See here. See here. Exothermic reaction. Exothermic reaction. Right now. So as the temperature increases, forward reaction becomes unfavorable, or the new equilibrium constant will decrease. New equilibrium constant will decrease. See here, new equilibrium constant at T2, they have given it as a Kp dash. Kp is at initial. Here, since it is exothermic, if you assume that T2 is more than T1, as the temperature increases, equilibrium constant decreases. So, the new equilibrium constant should be less than the initial equilibrium constant. New equilibrium constant should be less than the initial constant. Option E. You understood it? So they are given exothermic. Exothermic means as the temperature increases, what happens? Backward reaction becomes favorable, or the new equilibrium constant at higher temperature will be lower. K dash P dash is the new equilibrium constant. It should be obviously less than the initial, since it is exothermic. If it were endothermic reaction, it would have been the right answer. If it were endothermic, it would have been the right. They are giving that exothermic. Yes. Next one. Yes. Equilibrium constant. Yes. A2 to A, 500 and 700. 1 into 10 to the power minus 10. 1 into 10 to the power minus 1. Yes. Equilibrium constant is increasing, isn't it? With increase in temperature, equilibrium constant is increased. It was minus 10, it is minus 5, a little increase. So it cannot be exothermic, right? But the total value of equilibrium constant is very low, 10 to the power minus 5, 10 to the power minus 10. So it is not exothermic, but the reaction is slow. That much we can make out, because the very value of equilibrium constant is very low, 10 to the power minus 10, 10 to the power minus 5. So option B is the right answer. So it is a slow reaction, but not exothermic. If it were exothermic, the new equilibrium constant would have been lower than the first equilibrium constant. Right. See here. For the reaction X, Y, 3Z, right, they are given these quantities and these are the options. See, for a reversible reaction, QC will be there, KC will be there. Though the expressions are same for both QC and KC, QC you can find out at any time. KC you can find out only when the reactions attains equilibrium. Right now, we will find out QC. For this reaction, we will find out QC. Okay? Yes. The reaction is X plus Y giving 3Z. X plus Y giving 3Z. This is the reaction. Now, let me come to this. 3-liter vessel, 1 mole of X. So let me directly write the concentration. 1 mole of X by 3. 5 divided by 3. So to get the concentration, I have to divide the number of moles by the volume of the container. Next one is Y, how many moles? 2 moles. Its concentration will be 2 by 3. Next, Z is how many moles? 4 moles. Its concentration will be 4 by 3. Each number of moles are divided by the volume in liter, volume of the container in liter. Then let me write QC. Let me write QC. Okay. So expression is same. Z concentration to the power 3, X concentration, Y concentration. Let me substitute Z concentration 4 by 3 cube into 4 by 3 into 4 by 3. I made it like this, cube. Divided by X, Y. So into 3 by 1, because divided by, into 3 by 2, into 3 by 3, 3, 3, one more 3 gone, isn't it? If you simplify it, it will be 10.66. It will be 10.66. When the value of QC is 10.66, see here, when QC is less than KC, reaction proceeds in forward direction. If QC is equal to KC, reaction is at equilibrium. If QC is greater than KC, we can expect backward reaction. So in this case, we got QC 10.66. So the right option is the reaction will be at equilibrium if Kc is 10.66. Because here you got QC 10.66. So when Kc is, if it becomes 10.68, reaction will be at equilibrium. Option C is the right one. Option C is the right one. Okay? Yes. Yes. We will go to 27th. A vessel at 1000 Kelvin contains CO2 with a pressure of 0.5 atmosphere. Okay? Yes. A little carbon dioxide is converted into CO on addition of graphite. If the total pressure at equilibrium is 0.4, 0.8 atmosphere, the value of K is. Let me write the equation first. CO2 gas, they have added a little carbon which is solid. I shall write graphite. You get CO2, CO, which is a gas. Initial pressure is how much? Initial, they have taken it as 0.5 atmosphere. This is yet to be formed. This is solid. At equilibrium, you don't know, isn't it? At equilibrium. Okay? So of this, let X undergoes reaction. So X is the decrease. Okay? How much of this is used up? I should balance it. CO2 plus, correct now? Double of that carbon monoxide is formed. So if this is X, this formed is 2X. So pressure at equilibrium, 0.5 minus X plus 2X, it is 0.5 plus X. Pressure at equilibrium. They are telling that pressure at equilibrium is 0.8. So obviously, X becomes 0.8 minus 0.5, that is 0.3. X becomes 0.3. So partial pressure of carbon dioxide becomes 0.5 minus 0.3, that is 0.2. Partial pressure of carbon monoxide, that is 2X, that is 2 into 0.3, that is 0.6. Then how will you write Kp for this? Kp is equal to partial pressure of carbon monoxide of that square, 2 is that, divided by partial pressure of carbon dioxide. Okay. Carbon monoxide, it is a, how much we got? Partial pressure of carbon monoxide, 0.6. 0.6 square I shall write here only, divided by, what is partial pressure of carbon dioxide we got? Partial pressure of carbon dioxide is a 0.2. 1 za, 3 za, 3 into 0.6, 1.8. So right answer is 1.8 atmosphere. Option B is the right answer. 1.8 atmosphere. Option B is the right answer. Okay. Now let me, hope that it is clear. Okay. So initially 0.5. Out of that, let X undergo combination with this carbon. Okay. So double of that of this is formed as the reaction stoichiometry says. Then total pressure at equilibrium will be 0.5 minus X decrease plus 2X which is formed gas. This doesn't contribute to the pressure because it is a solid. So 0.8. So on solving x, we got it 0.3. So partial pressure of carbon dioxide, 0.5 minus 0.3, 0.2. Partial pressure of carbon monoxide is 2, double of that, that is 2x, 0.6. Then Kp you write, this you should ignore while writing the Kp expression. Substitute the value and then simplify, you will get it 1.8. Option B is the right answer. Option, yes. For the reaction H2, see the relationship is like this, delta G naught is equal to minus RT ln K or minus 2.303 RT log K. So this is ln, this is log. What they are telling you? Delta G naught is greater than 0. Delta G naught is greater than 0, means positive. Greater, if this is to be positive, minus sign is already there in the relationship, so this term should be negative. If the number k is less than 1, log of a number less than 1 is negative. So obviously it gets cancelled with this negative sign and you get the answer plus. So k should be less than 1. If k is greater than 1, log of a number greater than 1 is positive, then this sign remains as it is. So if this sign is to be cancelled, because what they need is delta G is greater than 0, positive. So k should be, what? K should be lesser than 1. K should be less than 1. Option D is the correct one. Option D is the correct one. Is the relation. Yes, we will move on to the last but one here. Last but one. Yes, see here. For the reaction, following option, which is correct for the stage half completion? When this reaction is half completed, 50% of A will disappear, 50% of B will be formed. So when the reaction is half completed, concentration of A will be equal to concentration of B in this reaction. So equilibrium constant will be 1. When the reaction is half completed, equilibrium constant is 1. When the equilibrium constant is 1, delta G naught is equal to minus 2.303 RT log to the base 10 of K. When the equilibrium constant is 1, log 1 is 0, obviously delta Z naught is equal to 0. When K becomes 1, delta G naught is 0. Option A is the right answer. Option A is the right answer. Yes, dear friends, we will move on to the last question. Yes. Hope that it is clear. Again, the last question is based on the same concept. For the reaction at 298 Kelvin, the equilibrium constant K is 200. The value of delta G. Delta G naught is equal to minus 2.303 RT log to the base 10 of K. Right. Minus 2.303 R. Here in calories, the final answer is calories. R value you have to substitute in calories only. R value in calorie, it will be 2 calories. 8.314 joule per Kelvin per mole. 0.0821 liter bar per Kelvin per mole. 2, exactly speaking 1.98, but we round it off to 2, so 2 calories. Then T is how much? T is 298 Kelvin into equilibrium constant is 200 log 200 minus 2.303 into 2 into 298 log 200 is 123, characteristic is 2 point, log 2 is 3010. This will be in calories. The answer will be in calories. But here the option given is in kilocalories. To get it in kilocalories, you have to divide by 1000. Understood why you have to divide by 1000? The answers given are in kilocalories, you have to divide it by 1000. If you simplify, it will be minus 3.158 kilocalories. You understood why I have to divide by 1000? Because the options given are in kilocalories. Minus 3.158, option C is the right answer. Option C is the right. So dear friends, like this, simple questions will be asked. So what you have to do is, all the questions again solve independently and try to get correct answer. Okay. So wish you all the best. We'll meet in the next section for ionic equilibrium. So thank you. On and on.